Okay, so welcome to this webinar. I'm Jenn Wortman Vaughan, a senior principal researcher here at Microsoft Research in New York City and part of the FATE research group here at MSR. Today I'm going to be talking about transparency and intelligibility throughout the machine learning lifecycle. I'll also be doing a live Q&A session after this talk, so if you're watching this initial broadcast live, please feel free to submit your questions at any time. All right, so if you found this webinar, I don't think I need to waste time convincing you that machine learning is important. But throughout this talk, I'm going to be arguing for the importance of taking a human-centered view of machine learning. We often think about machine learning as this fully automated process. We take some data, use it to learn a model, and out come our automated predictions. But one thing that I've learned over the years is that people are at the heart of the machine learning lifecycle. People define the task that machine learning is going to be used to solve. People decide what data to collect. They decide how to clean and pre-process the data and how to label it. And the data itself is often generated by people, either explicitly, for example, through crowdsourcing, or implicitly, for example, if the data contains text written by people or images of people. People determine what model to use, say a neural network or a decision tree or a linear model. People choose how to train this model, how to test the model, which may again require gathering more data from additional people. People make choices about whether, where, and how to deploy this model. And of course, deployed models end up impacting people's lives, sometimes in high-stakes domains like medicine or finance. Finally, feedback from these people is incorporated as the model evolves. Given the central role that people play in the machine learning lifecycle, I take the position that building machine learning systems that are reliable, trustworthy, and fair requires relevant stakeholders to have at least a basic understanding of how they work. This view is reflected in Microsoft's core principle of transparency, one of our 6 AI principles. And it's something that I think about a lot personally as the co-chair of Microsoft's Ether working group on intelligibility and explanation. This working group is part of our broader Ether efforts on programs, policies, procedures, and best practices on issues to do with AI, people, and society. But you might ask, what exactly is transparency? Well, okay, people use this term transparency in all sorts of different ways, and I'm not going to attempt to end this debate once and for all right here. So let me just tell you what I mean when I talk about transparency. I find it really useful to break transparency into 3 components. This breakdown is adapted from one that was proposed by the European Commission's high-level experts group on AI last year, and I like this breakdown a lot. So first of all, transparency relies on a foundation of traceability. This means that teams should clearly document their goals, definitions, and design choices, and any assumptions that they've made. Now, I happen to be someone who gets very excited about documentation, and I know that not everybody out there shares this excitement with me, but I still want to take a few minutes to talk about traceability because I think it's really important. I'm going to start with data because data plays such a central role in the machine learning lifecycle and the machine learning models that we build. About 2 years ago, a group of us at Microsoft Research in New York started a project called Data Sheets for Datasets. Inspired by data sheets for electronic components, we proposed that every dataset be accompanied by a data sheet that documents relevant information about the dataset's creation, its intended uses, its limitations, and so on. Datasheets can help dataset creators uncover possible sources of bias in their data or unintentional assumptions that they've made. They can help dataset consumers figure out whether a dataset is right for their needs, whether it will be useful for a model that they're trying to build. And if exposed either in whole or in part to end users, they can help end users figure out how much they should trust a system. So we've been piloting datasheets across Microsoft, and from early pilots, we've updated our idea of the types of questions that a datasheet should include. And you can find a full list of the questions that we recommend in our paper on this topic. We've got questions on the motivation for a dataset, its composition, the collection process, any pre-processing or cleaning or labeling of the data, the intended uses of the data, and perhaps uses that it should not be used for, the distribution of the data, and also maintenance. Questions about ethical and legal considerations are peppered throughout all of these sections. We've also constructed a new proposed workflow so that each of these sets of questions can be answered at a specific different phase of the dataset's life cycle. Now, there are actually a huge number of research challenges that have come up during our pilots, and I'm going to mention just a few. So some are to do with the specific questions that we ask. For example, how should these questions be modified when the data set that we're looking at consists of streaming data instead of static data? There are also a lot of questions around workflows and incentives. But one thing that we've learned along the way is there's not going to be a one-size-fits-all solution here, and different teams are going to need to modify this type of proposal to fit their own needs. But given the central role that data plays in machine learning, the payoff for getting this right, we think, is potentially huge. In parallel to these internal efforts at Microsoft, we're collaborating with the Partnership on AI, which is a multi-stakeholder institution that's dedicated to studying and promoting best practices for AI. Last spring, the partnership launched a project called About ML, which is dedicated to applying transparency to all components of the machine learning lifecycle. To make this happen, the project is building off of data sheets for datasets, as well as other related proposals like the Data Nutrition Project at MIT, Google's model cards, and IBM's fact sheets. So one way that all of you can get involved is to create your own data sheets when you release datasets online. We've actually started seeing some awesome examples of researchers including a data sheet as part of a paper, either as an appendix or maybe through a separate link. And I would love to see this become a community standard, so please help us make this happen. Okay, moving on. The second component of transparency is communication. Those who build and use AI systems should be forthcoming about when, why, and how they chose to build and deploy these systems, as well as the system's limitations. Datasheets are, of course, relevant here too if you think about how they might be tailored to help this third population of stakeholders, the end users of a system. Another way that we're thinking about implementing communication at Microsoft is through what we call transparency notes. So for example, last spring, Microsoft released a transparency note for our face recognition API. This is this publicly available document that details Face API's capabilities and limitations. It includes a discussion of how users should interpret different accuracy measures, like false positives and false negatives, and some examples of how a team might choose to trade off these accuracy measures against each other in different applications. This is also related to things like model cards and fact sheets, and it's also something that academics who are releasing machine learning tools might implement as well. So I encourage people to think about things like this more. Okay. Finally, the third component of transparency, and the one that I'm going to spend the most time on in this talk, is intelligibility. Intelligibility means that people should be able to understand, monitor, and respond to the technical behavior of AI systems to whatever extent necessary to meet their specific goals. This is sometimes referred to in the machine learning community as interpretability. And the European Commission, which I mentioned before, refers to it as explainability. I've actually used the phrase interpretability a lot in my own work, including some of the papers that I'm going to talk about today. But for the rest of this talk, I'm going to stick with the term intelligibility. Personally, I like this term the best because it has roots in the HCI community, and to me at least, it kind of emphasizes that we're talking about a human-centered concept here, right? Something can't really be intelligible without being intelligible to someone. So why should we care about intelligibility? Well, there are a whole bunch of different stakeholders of machine learning systems that can benefit from it. So let me just give a handful of examples. So intelligibility can improve the robustness of an AI system by making it easier for data scientists and engineers to identify and fix bugs, and I'll come back to this particular use case later. Intelligibility can help doctors or CEOs or any other decision makers using a system decide when and how much to trust this system, and hopefully this will eventually lead to better outcomes. Intelligibility allows designers to reason about how systems and models behave so that they can appropriately convey this information to end users. Intelligibility around key characteristics of a data set that's used to train a model can potentially uncover sources of bias or unfairness in the data that will make their way into the model. Intelligibility can help demonstrate compliance with regulatory obligations, so things like GDPR potentially. Intelligibility enables new tools to help scientists who are developing models make hypotheses about their world. And just generally, intelligibility leads to more usable products. So the approaches to model intelligibility that are coming out of the machine learning community generally fall into two categories. The first type of approach is to design and deploy models that are intuitively simple. So simple here might mean something like a small decision tree or a sparse linear model, for example. My colleague Dan Goldstein and his collaborators have some really nice work on simple point systems that a decision maker, such as a judge, could potentially memorize and apply on the fly without even a need for pencil and paper. And they actually show that, perhaps surprisingly, in many high-stakes domains, at least those where we're talking about tabular data, these point systems are nearly as accurate as more complex models like neural networks, so there's no loss there. As another example, Rich Caruana has a body of work on generalized additive models, or GAMs, that falls into the same category. The reason that GAMs are nice is that their predictions have this additive structure, which allows users to visualize the impact of a single feature. So you have one function that's corresponding to each feature, and you can visualize that function in order to see how the feature is affecting your output. Remember this because I'm going to come back and talk more about GAMs a little bit later. All right, so the second common approach in the machine learning literature is to design simple post hoc explanations for complex models. So you may have heard of LIME or SHAP, and these would fall into this category. So many of these approaches work by approximating a complex function using some sort of simple local approximation, like a linear function that can be easily explained. SHAP, which I'm also going to come back to later in this talk, builds on ideas from cooperative game theory to assign an importance to each feature, which You can think of intuitively as a measure of how much that particular feature contributes to a prediction for that particular data point. If you're interested in playing around with some of these approaches, I'll give a quick shout out here to the Interpret ML open source package, which was released by some of my colleagues at Microsoft earlier this year. And I'll mention that Azure ML also offers similar functionality. So those are both great resources to look at. But despite all of this really cool research that's going on and these tools that are being built, there's actually still a fair amount of disagreement in the machine learning community about what intelligibility actually means and how to measure it. Looking at all of these proposed approaches, it's really natural to ask what makes a model or an explanation simple, and how is simplicity related to intelligibility? And do these models actually help users achieve their goals? So there have been a couple of position papers examining this issue over the past couple of years, and as Finale Doshi Velez and Bean Kim point out in theirs, the machine learning community often has this "you'll know it when you see it" type of attitude around intelligibility. The difficulty of defining and quantifying intelligibility is compounded by the fact that there are different stakeholders out there, and these different stakeholders or users have different needs. The approach that works best for a CEO who's making a strategic decision is likely to be different from the approach that works best for a regulator who wants to understand why an individual is denied a loan. And this, in turn, may be very different from what a data scientist needs when they're trying to debug a model. On top of all of this, all of the approaches that I've mentioned so far have focused on intelligibility of the model itself. But if you think about this bigger picture of the machine learning lifecycle that I mentioned earlier, model intelligibility is just one piece of this bigger picture. Depending on who our stakeholders are and what goals these particular stakeholders have, we may want to introduce intelligibility at other stages of the machine learning lifecycle, starting from the definition of the problem or task that is being solved, through data collection and all the way to intelligibility around model deployments and feedback. So these concerns have prompted me to adopt a human-centered agenda for intelligible machine learning. And I should tell you here that I am a learning theorist by training, so it has taken me a long time to get to this point in my career. My colleague Hannah Wallach and I have actually written a book chapter on this, which should hopefully be online by the time you're watching this webinar, so I would encourage you to check this out if you're interested in kind of more detail on how we envision this. But within our research group, we've been working on this agenda from several angles. So first of all, we propose that people stop relying on intuition and instead empirically test which factors of a model enable users to better achieve their goals. And in a few moments, I'm going to tell you a little bit about some work we have in this space that examines how factors commonly thought to influence intelligibility actually impact people's use of a model. A second angle to consider here is intelligibility beyond the model. So, for example, intelligibility of data or intelligibility of objectives or performance metrics. And I'll tell you about some work that we have in the space examining how the stated and observed accuracy of a model impacts people's trust, which we view as a study on intelligibility of performance metrics. Finally, we propose that people design and evaluate methods for achieving intelligibility in context with the relevant stakeholders. And here I'll tell you some more about some very recent work examining how data scientists perceive and use intelligibility tools. Okay, so jumping right into this first point, to question our intuition about intelligibility and empirically test this intuition, my colleagues and I found it helpful to think about intelligibility as a latent property that can be influenced by different manipulable factors, such as the number of features of a model, whether the model is linear, the user interface of the model, whether the internals are exposed, and so on. And that, in turn, impacts different measurable outcomes. So things like a user's trust in the model, how willing they are to follow a model, their ability to debug the model, or perhaps their ability to simulate the model. Now notice that all of these properties on the left here are properties of system design, whereas on the right we have properties of human behavior. So taking a cue from psychology, to study this, we designed randomized human subject experiments to isolate and measure the impact of these different system factors on fundamental properties of human behavior that are pertinent to intelligibility. So the idea is basically to randomly vary these factors like the ones on the left, and then measure their impact on human properties like the ones on the right. While this may sound like it's something that is very simple to do, in practice, it's really hard to do this while holding all other factors of a model equal. And this is kind of the contribution of our way of thinking about this. So in our first set of experiments on this topic, participants were asked to make predictions about the selling price of different apartments with the help of a model. So in addition to a simple baseline where participants didn't actually have access to a model at all, we considered 4 experimental conditions in a 2x2 design. And these are corresponding to the 4 models that you see here. So I don't expect you to be able to read everything on these slides, but let me point out the differences between these conditions. So first, the models on top make use of only 2 features, while the models on the bottom make use of all available features. Additionally, the models on the left are presented as a black box with no information about what the model is actually doing, while on the right you see transparent linear regression models with weights that are visible to participants. And for these conditions on the right, we explained during a training phase exactly how these models work to make sure that participants understand. Now, crucially, in all of these conditions, participants see the same model input, so everyone sees exactly the same features of these apartments. They also see the same model output or predictions. So that is, we specifically chose a set of apartments where the 2-feature and 8-feature models that we are using made the same predictions. This means that the only difference between these randomized conditions in what people see is what's in between. So if we observe any differences between these conditions, we can safely attribute these differences to the model and what we're showing them. So this is kind of super important in our design. So I'm not going to go through our studies in detail, but I just want to mention a few key results from this study and some of the implications of these results. And I'll point you at our paper if you're interested in learning more. So first, we found that participants who were shown this clear model with a small number of features, 2 features in this case, were best able to simulate the model's predictions. So this is perhaps unsurprising, but it's reassuring to see this play out in the data from our experiment. However, we found no improvements in the degree to which participants followed the model's predictions on typical examples when it generally actually would have been in their best interest to follow the model. Additionally, we found that in some cases, too much transparency can actually be harmful. So specifically, we found that transparency reduced people's ability to detect when a model is making a sizable mistake and correct for this mistake, seemingly due to information overload. So this was really surprising for us and did not kind of match our intuition about what was going to happen here and the popular belief in the machine learning community. So more generally, these results just emphasize the importance of user testing and experimentation over reliance on intuition alone in the design and evaluation of intelligible models. Okay, moving on to the second direction, intelligibility beyond the model. Let me briefly describe some work of ours that appeared in CHI this past year that can be viewed as a study of intelligibility of performance metrics. So in this study, we set out to examine whether a model's stated accuracy on held out data affects people's trust. If so, whether it continues to do so after people have had a chance to observe the model's accuracy in practice. And finally, how a model's observed accuracy in practice affects trust. To do this, we again made use of randomized human subject experiments. We showed subjects information about pairs of people who had been matched together through a speed dating event. And we asked them to predict whether these people were interested in seeing each other again based on this data that we presented them with. In particular, subjects were asked to make their own predictions about whether a particular speed dating participant wanted to see this particular partner again. So they were then shown a prediction from the model after making their own prediction and were given a chance to revise their prediction in light of what the model said. So they did this many times, completing 40 such tasks in 2 phases. So at the beginning of the first phase, we gave them information about the model's accuracy on held out data. Then, after the first phase, which consisted of 20 of these tasks, we gave them feedback on how they themselves and the model had performed so far. So they got information about both their own performance and the model's performance on the first 20 tasks. And at the end, we had them answer a couple of questions about their use of the model. In each of our experiments here, we varied either the stated accuracy of the model, which we told them at the beginning, or the observed accuracy of the model on the first 20 tasks, or some combination of the two. Okay, so again, I'm going to just skip right to the high-level results and implications and point you at this paper if you want to learn more. So first, we found that the model's stated accuracy on held-out data does affect people's trust in the model. And specifically, they are more willing to depend on the model when its stated accuracy is higher. We also found that people put substantial weight on their own interactions with the model in the accuracy that they observe. We saw this happen even though the subjects in this experiment had somewhat limited interaction with the model. That is, they changed their behavior after getting information about the model's performance in phase 1, which only contained these 20 tasks. So these and other results that we also discuss in our paper really highlight the need for designers of machine learning systems to clearly and responsibly communicate their expectations about model performance. We see here that this information that's communicated to users really shapes the extent to which they trust a model, both before and after they observe the model's performance in practice. So it's important to get this right. Okay, So moving on to the final bullet here. I'll spend the next few minutes talking about some very recent research, looking at how we can evaluate the intelligibility of existing tools with stakeholders in context. This work was led by an incredible summer intern, Harman Kaur, and depending on exactly when you view this webinar, I'd say that there's about a 90% chance that you should be able to find our paper online. So in this work, we're zooming in specifically on data scientists who are building models as our stakeholders of interest. In particular, we're interested in looking at how data scientists use and perceive existing off-the-shelf intelligibility tools. We're interested in the challenges that they face in doing this, and we're interested in the opportunities that we, as the research community, have to make these tools better. So before I get into the details of our study, I want to take a step back and talk for a little bit about why this type of evaluation is challenging. And I want to be really super clear here that the reason that this type of evaluation is often missing from machine learning papers is not because machine learning researchers are lazy or just don't care, but because getting this type of evaluation right is really a research agenda on its own and not something that's trivial. So first of all, doing this right requires expertise in both the details of the machine learning models and intelligibility tools, as well as expertise in HCI or psychology or other human-centered fields. It requires knowledge of both the academic literature on these tools, as well as the day-to-day engineering practices of data scientists. It requires both a qualitative analysis that's useful for understanding the nuances of how people use these tools in context, as well as quantitative methods so that we can yield more reliable and scalable findings. A good study here should mimic realistic data analysis settings, yet it can't be too cumbersome. For example, in this work, we were trying to limit ourselves to a study that people could complete in 1 hour. And finally, it requires being able to separate effects of the model from effects of the intelligibility technique that's used, from effects of the user interface of the specific tool. And these are things that can be really challenging to tease apart. So this is not something that it's generally easy to do. We tried as best as we could to address these challenges, although no study here is going to be perfect. So first, to address these challenges, we recruited a diverse team to work on this project, consisting of both a mix of machine learning and HCI researchers, as well as data scientists who actually have day-to-day experience both building and using intelligibility tools. We also attempted, as best as we were able, to put the data scientists that we studied into a somewhat realistic context, which I'll tell you more about shortly. And finally, we did apply a mix of qualitative and quantitative methods. So specifically, we started with pilot interviews, which we used to qualitatively identify challenges that are faced by data scientists in their day-to-day work. We then performed a contextual inquiry, which you can think of as a structured interview in context to observe data scientists' ability to use these tools when faced with the challenges that we identified. This, again, was a purely qualitative analysis. And finally, in order to scale up these results, we ran a large-scale survey with around 200 participants, which we designed to try to mimic the contextual inquiry as best as we could. Okay, so to reiterate, our goal here was to evaluate data scientists' use of existing intelligibility tools to address their day-to-day challenges of building and evaluating machine learning models. So our first step then must be to understand the types of challenges that data scientists face, or the context in which they're going to use these intelligibility tools. This was the goal of our pilot interviews. From these pilot interviews, we extracted 6 common challenges. So missing values in the data, redundant features, duplicate data that's masked as unique, temporal changes in the data, ad hoc categorization of feature values, and challenges recognizing patterns that will help with debugging. I'll come back to some of these in a moment. Building on these challenges, we designed a contextual inquiry, which again is essentially a structured interview in which we try to place participants into context. In this case, working with real data, a real model, and a real intelligibility tool. We wanted to explore the use of both of these types of approaches that I mentioned earlier, so both simple models and post hoc explanations. So we chose one example of each and had half of our participants using generalized additive models, or GAMs, and half of our participants using SHAP, the post hoc explanation technique. We began the contextual inquiry with a pre-study interview about the data scientist's prior experience and expertise before moving on to the main study, and ended with a series of follow-up questions. For this study, participants were given a Jupyter notebook that we had already set up for them. They first saw a tutorial on the intelligibility tool that they were going to be shown, which was based on existing published documentation with a bit more detail that we added ourselves. They then saw an introduction to the data set, which was a modified version of the popular adult income data. I'll talk about how we modified it in a moment. They saw a little bit about the model and were given a chance to play with some of the model's visualizations. And they were then asked a series of questions about the data in the model. So each of these tools, GAMS and SHAP, provided 3 types of explanations. The first is local feature importance. So this is a description of how important each feature is for the prediction that's made on a specific individual data point. The second is global feature importance. So how important is each feature on the whole across the entire data set? And these actually look very similar for the 2 approaches. The third type of visualization zoomed in on the way that a specific feature, so age in this example, impacts predictions. So as I mentioned before, we use this modified version of the adult income data set. Specifically, we modified it to reflect the types of challenges that we extracted from participants during the pilot study. So for example, data scientists often face problems due to missing values in the data and the way that these missing values are filled in. So before training the model, on 10% of the data points where the label was positive, which in this case means that the person represented by the data point makes more than a certain amount of money, we removed the age value and used the common approach of replacing it with the mean across all of the data set, which in this case was 38. And this resulted in the model exhibiting this strange jump in predictions for 38-year-olds. As another example, to capture ad hoc feature categorization, we took one feature, which is the number of hours that someone works in a week, and binned the values into these somewhat nonsensical categories of 0 to 30 hours, 30 to 60 hours, 60 to 90 hours, and 90 plus hours. So most of the data points fell into this 30 to 60 hour bucket. Okay, so a couple of different themes emerged from our qualitative analysis of the interview data from this contextual inquiry. First of all, we found that there's a set of participants who overuse the tools. using them to justify cases where the model exhibited strange behavior. And this led them to place too much trust in the underlying machine learning model. So as one participant who was given GAMS said, age 38 seems to have the highest positive influence on income based on the plot. Not sure why, but I guess if that's what's shown, makes sense. Another participant who was given SHAP ran some of their own tests and was willing to accept the model's behavior when this participant found that their own test agreed with SHAP's output. Saying test of means says the same thing as SHAP about age, all's good. On the flip side, we saw some cases in which participants underused the tools because they weren't confident about exactly what the tool was showing them. So as one example, a participant who saw SHAP said, the tool assigns a quantity that is important to know, but it's showing that in a way that makes you misinterpret that value. Now I want to go back and check all of my answers. After going back and playing around with the data some more, the participant continued, okay, so it's not showing me a whole lot more than what I can infer on my own. Now I'm thinking, is this an interpretability tool? Another theme that emerged was the importance of social context. So in particular, participants seemed willing to trust what the intelligibility tools were telling them because they were publicly available tools. And they said this very explicitly. So one participant said, I guess this is a publicly available tool, must be doing something right. I think it makes sense. And another said, I didn't fully grasp what SHAP values were. This is a pretty popular tool, and I get the log odds concept in general. I figure they were showing SHAP values for a reason. Maybe it's easier to judge relationships using log odds instead of predicted value. Anyway, so it made sense, I suppose. Okay, so we thought these qualitative results were super interesting and a bit worrisome. But we wanted to scale up our findings. So we designed a survey to attempt to replicate the contextual inquiry setting at scale as best as we were able. The survey began with some questions about demographics and experience, just as the contextual inquiry did. And then, since participants would not be able to interact directly with a Jupyter notebook anymore, we showed them screenshots of common ways in which the contextual inquiry participants had chosen to explore the dataset, model, and tool. So we tried to kind of simulate this interaction, even though it's not perfect. Finally, we asked them a bunch of questions about the dataset, model, and tool that they were supposed to answer based on screenshots of visualizations that we showed them. We took advantage here of having a larger pool of participants to run some randomized controlled experiments in our survey as well. So we randomized two things. First, as before, we randomized whether a participant would use generalized additive models or SHAP. And second, in order to understand how people were affected by the content of the explanations, we randomly showed half of our participants a manipulated version of the global feature importance values instead of the actual visualization. So in particular, on the left here, we have the global feature importance plot that would be shown to participants in the normal condition. On the right here, we have the plot that is shown to participants in the manipulated condition. This is identical, except we've swapped around the order of the features here, so which feature corresponds to which bar, with the results that the unimportant features are shown as important and the important features are shown as not important. So our qualitative findings on the whole were similar to what we saw in the contextual inquiry, though some additional themes emerged. So for example, even though we showed tutorials, very few participants could accurately describe the visualizations beyond a superficial level when we directly asked them what the visualizations were showing. So by a superficial level, I mean some would say something like feature importance, but not give any detail on what feature importance actually means. We also saw that participants often use these visualizations to craft their own narratives in order to convince themselves that the model was reasonable. So for example, one said, plot B looks reasonable since it provides a bonus to individuals in working age range and penalizes others. It also correctly considers widowed people to be more likely to earn more since they are more likely to inherit assets. So this is not really what's going on here, but people crafted their own narrative about what they thought the underlying model might be reflecting. And again, we're kind of seeing here that some participants seem to actually increase their trust in the underlying model just because they're being shown an explanation, right? We would hope instead that people seeing this explanation would become suspicious of the underlying model, but that's not what's happening. So in our paper, we explore all of this qualitative data much more if you're interested. But I want to mention some of our quantitative comparisons now. So in particular, we pre-registered 8 different quantitative comparisons that we wanted to make between these different randomized experimental conditions. So for 3 of these, we did see significant differences between participants who saw GAMS and participants who saw SHAP. Specifically, participants who used GAMS had higher accuracy on the multiple choice questions they were asked about the visualizations that they saw. They also had higher self-reported confidence in their own understanding of these visualizations. And participants who saw GAMS had a lower cognitive burden as measured by a standard NASA TLX cognitive load index. So putting these 3 results together, this is kind of all evidence that participants found GAMS somewhat easier to use than SHAP. The results for self-reported confidence that the model was reasonable are actually very reassuring. So here we saw that people who saw the unmanipulated or normal version of GAMS were more confident that the model was reasonable than people who saw the version with manipulated visualizations. And the same was true for SHAP. So this is good because it tells us that people are paying attention to the actual content of these explanations, at least to some degree. We also found that people who saw the manipulated version of SHAP were more confident that the underlying model was reasonable than people who saw the manipulated version of GAMS. So this is kind of further evidence that GAMS may be easier to work with in some sense than SHAP. People were more able to recognize that something a little bit fishy was going on with this visualization. However, for the other 4 quantities that we looked at, self-reported confidence that the explanations were reasonable, the extent to which participants rated the model as ready for deployment, whether people expressed suspicions about the model, and whether people expressed any suspicions about the intelligibility tool itself, we saw no significant difference between conditions at all. So we saw no difference between GAMS and SHAP here. We also saw no difference between people who saw the normal visualizations versus people who saw the manipulated visualizations. So this work suggests several next steps for the research community that I'd like to highlight here. First, we really need more interaction between machine learning and HCI researchers. And we need this interaction to be happening much earlier, at earlier stages. Human-centered approaches should be incorporated into the design and the development of these intelligibility tools in the first place, in addition to their evaluation. Second, we need more tools that are designed specifically to encourage deep thinking and discourage people from making snap judgments. Actually, one of our study participants put it really nicely, saying there's this concept in UX called thinking fast and slow. While these visualizations made me think fast, every detail about them requires that I think slow. Finally, in our study, as I mentioned before, we are aiming for each participant to only have to spend about an hour engaging with the tool. And really, the community is going to need more longer-term studies in order to explore how people's understanding and usage of intelligibility tools changes over time as they become more comfortable about the tools and learn whether to trust them and when and how to use them. Hopping up a level, I've told you about studies that we've run on lay people and studies that we've run on data scientists, but there are many other stakeholders out there who might require intelligibility. And one really huge, wide open direction in this space is to better understand the needs of these stakeholders and how to design intelligibility approaches to help them. And finally, as I've been arguing throughout this talk, we need to take a broader view of intelligibility and think about how to bring intelligibility and transparency more generally to every stage of the machine learning lifecycle. All right, so thank you all so much for watching this webinar, and I hope that you found it useful. If you're watching the initial broadcast, I look forward to taking your questions in the live Q&A session that's about to start. And you can check my website for links to many of the papers that I mentioned during this talk if you're interested in learning more. So thank you again.
Okay, hi everyone. So thanks so much for attending the webinar today, and thanks especially to everyone who submitted questions. I'm Jenn Wortman Vaughan. You've just been listening to me speak for the last 52 minutes or so, but now I'm here live to answer a couple of questions. So let's jump right into that. Okay, so our first question today is one that I get asked a lot, and it's more of a personal question. So as I mentioned briefly, my background is in machine learning theory and algorithmic economics, which are very theoretical, mathy areas. So how did I end up incorporating all of these techniques from HCI and other human-centered fields into my work? So this is a great question. So often in academia and in research, just because of the way that incentives work around hiring and around tenure and all of that, people end up getting boxed into one specific research area or one specific methodology and sticking with it. The thing I've done in recent years that's led to the biggest impact on my career and on my own satisfaction with my research is to kind of smash that box apart. So I can trace my interest in human factors back to a specific panel discussion I attended back in 2016. It was one of these panels on AI and society that are happening all the time now. And one of the panelists made this comment that stuck with me. He said, and here I'm going to paraphrase a bit, soon our AI systems will be so good that all of the uncertainty will be taken out of our decision making. And I heard this and thought, wait, what? The world is inherently full of uncertainty. All of our AI systems and machine learning models have uncertainty baked into them, whether it's explicit or not. To me, it just seems totally irresponsible to tell people that AI could take uncertainty away. So I came back to New York fuming about this comment. This was around the time that there started to be a lot of talk about democratizing AI, making it easy for lay people to build or deploy their own machine learning systems. For context, it was also around the time that Hillary Clinton's chance of winning the US election was hovering around 80%, and the general public was treating this as a done deal. And watching all of this play out and replaying this panelist's quote over and over in my mind, I became obsessed with the question of how well people really understand the predictions coming out of models. As a theorist, I was trained to always state my assumptions clearly and explicitly, and this is something that I thought about a lot. I was afraid that people may not always understand the implications of the assumptions that go into machine learning models or the uncertainty behind any prediction. These worries led me to discover this literature that was just starting to come out of the machine learning community on intelligible or interpretable machine learning, some of which I mentioned in my talk a few minutes ago. And I got really hung up on the fact that people were designing these methods without stopping to define exactly what they mean by interpretability or intelligibility, basically proposing solutions without first stopping to define the problem that they were trying to solve. So I started talking about this problem with colleagues with backgrounds in psychology and computational social science and other human-centric fields, and we decided to do something about it. Since then, I've gotten more and more passionate about these issues, and I've also started working in the space of fairness a lot more. So fairness is another area where it's crucial to consider the humans who are involved. And the more that I get involved in this line of work, the more it seems to be the case that the problems I'm most excited about are not problems that I can address with theoretical models or with new algorithms alone. They're the problems for which I really need to use human-centered techniques. So solving these problems means that I have to kind of break out of my box. I just have no choice if I want to do this work. And I've been having a great time doing it. By the way, one approach that's worked really well for me here is hiring research interns who have expertise in running user studies and conducting interviews and all of this methodology that's outside my own formal training. So I'm always looking actively for PhD candidates in the space who have training in HCI or psychology or other related fields and are interested in collaborating with machine learning researchers. So if that is you, please drop me a line. Okay. Let's see. The next question I have here that I want to answer is about data sheets, model cards, and other related documentation-based approaches. So I very briefly mentioned that incentives can be an issue here. So in general, busy people aren't motivated to spend a lot of time on documentation. So what can we do about this? This is definitely one of the biggest challenges around making processes like data sheets and model cards the norm. And actually, I think this issue of incentives and priorities is something that goes beyond documentation to processes around responsible AI more broadly. So I have an upcoming CHI paper with Michael Medeo, Luke Stark, and Hannah Wallach, in which we looked at checklists for fairness in AI. And in particular, went through the process of co-designing an AI fairness checklist with machine learning and AI practitioners in industry. So during this process, we uncovered some organizational challenges that practitioners face that would influence their ability to adopt checklists. And I think these challenges are very similar to those that come up when we're talking about adopting data sheets or model cards or any of these approaches. So for example, participants in our study who came from a variety of different companies felt that these types of in order for these types of processes to succeed, it was crucial to have organizational buy-in, especially from leadership, and to have all of these practices around responsible AI built into the metrics or key performance indicators and so on that they're getting judged on, so that people actually get credit for this type of work. They also felt it was crucial to adjust these processes to fit their existing workflows and processes that they already have. So this was all really eye-opening for me because when we started the Data Sheets project, my collaborators and I had this grand but somewhat naive in retrospect vision that we would have a set of questions around data, and this would be the right set of questions for everyone to answer, and we would create a nice template for these and kind of be done with it. But in reality, there are almost never one-size-fits-all solutions for this type of process. And in addition to figuring out how to get the incentives right for different groups, we need to figure out how to help teams adapt processes like data sheets to their own needs. These are questions that I'm really interested in and things that the Partnership on AI is thinking about quite actively too. Okay, I think we have time for one more question. So given the results of the final study I talked about, what do I recommend for data scientists who actually want to use intelligibility tools today? Another good question. So I actually think that the existing tools like InterpretML can be really valuable and useful to data scientists as long as the people using these tools exercise appropriate caution and skepticism. So we've seen in our study that data scientists can end up placing too much trust in a model simply because they've been provided with an explanation of its predictions, and this is something we want to avoid. But there are ways that these tools can be used to help data scientists figure out when they should be skeptical. And I've seen data scientists use these tools in this way with great success. My colleague and collaborator, Rich Caruana, has countless anecdotes about times that he's used GAMs to uncover surprising characteristics of data sets, including a real-life example that served in part as motivation for what we did with the age feature in the study that I talked about. One suggestion I'd make here, concretely, is not to rely too heavily on any one type of explanation, since they're all imperfect. So for example, it can be quite eye-opening to run both LIME and SHAP on the same data sets and the same predictions and compare what features they output as important. In my own experience, these can be quite different. And this gives you a sense of perhaps which features are more important and also how much trust to place in these explanation techniques. But more broadly, I think there is still a bunch of really fascinating open research questions on how to make these tools more helpful to data scientists, and this is a line of work that I am generally really interested in pursuing. Okay, great. So I think that is all we have time for today, and that is the end of our webinar. So thank you all so much for attending. If you're interested in learning more, we've listed some great resources in the resource list, which I believe should be on the right side of your screen, and it's also in the email that you received. So this resource list includes, among other things, all of the main papers that I talked about today. They did indeed make it online in time. And I look forward to seeing how you all go and build on this research and evolve the space of intelligibility and machine learning. Have a great day, and thank you so much again for attending.